let's continue our discussion of charts and graphs, and maybe we're not going to discuss all of them, but we're going to sort of go through a couple ones that are of interest. So last time we had talked about histograms, and we had discussed the idea of a normal curve. So it was mound-shaped. It went up and it went down. We'd also talked about skew, and of course before that we talked about proper ways of collecting data. So we're going to sort of continue with this idea of organizing data, and this is part of something called Exploratory Data Analysis. EDA for short. So let's talk a little bit about an idea first of all. In general, it is very easy to spend hours, years, centuries analyzing data. You can always do a little bit more analysis, go a little bit further, try some other techniques. Anytime you model something, and that's what statistics is, we're trying to model the world around us, you accept certain things as being too complicated for the model. You accept other types of modeling processes as being irrelevant or, again, too time-consuming because you want actionable information. It's the difference between deciding that a cup of water is enough or saying, let's try to drink a whole ocean. You can always go further, and so in an effort to maybe sort of get some initial ideas to decide, do I even want to go really any distance at all, we have what we call exploratory data analysis. And one of the first things we care about in this class is whether things are normal. Because most of the math I'm going to teach you in this course is specifically designed for things that have that normal bell shape. And the first question you might ask is this random data I've got normal? And so to do that, let's take a look at what we call a stem and leaf plot. Stem and leaf displays are some of the most simple charts that you can create. No real craziness with talking about class limits. That's nice, it's great, but stem and leaf is faster and easier. As my students turn in exams and I start to want to doodle with the grades and figure out what it looks like this semester, I'll probably be in the back sketching a little bit of a stem and leaf plot. It is the fastest and is one of the oldest ways to model data. And here's how it works. You first look at your data and you see what are the highest numbers. And think back maybe, I don't know, third grade or something, where you had the hundreds column, the tens column, and the units column. And here I see that, yeah, I've got some numbers like 1, 9, and 8, but in general, I have numbers that have 2 digits. Tens column is the biggest. So here's how stem and leaf plots work. You have the stem, think of a tree, you've got the stem, and then off of the tree branches some little leaves. So my stem is going to be all the highest numbers that I've got. In my case, 2 for 28, and 4 for 49, and 5 for 57. Let me go ahead and rebrand 8 as 08, 09, 01. That'll tell you how the stem works. And then what you do is you build a stem. I've got zeros, 1, 2, 3, 4. I see 5s, I don't see any 6s up here, so 0, 1, 2, 3, 4, and 5, I think is as high as my stems need to go. And then what I do is I go through my data one at a time, and I take a look and I say, okay, I've got 28, this goes in the 2 column, and I've got the number 8. So I record the 8. Notice I just write the 8, and I cross this guy off. I've got the number 8, that's in the 0 thing, I record the 8 here as well and cross him off. Next I have 49. I record the 9 here and cross him off. And then I have 57, so I record a 7 and cross him off. And next I have 54, so I record the 4 and cross him off. See how it's going? I'm starting to build up and see what I've got here. 46 is another 6, so I record that. Notice these are not in order. 9 is before 6, 7 is before 4. We know that this is 49 and this is 46 because these are all in the 4 columns. And I can start to see how my chart's going. Keep on up with it. Another 8. 25 now. 41. 39. The first 30. 37. The number 9. So far this part's in order. 31. 40. I record a 0 here for the 0 the 40. 49. I record another 9. 54. 25, again, 42, 52, 19, 1, another 19, 22, 14, and 46. This is called an unordered stem and leaf plot, and if you turn your head on the side and look at it, this looks like one of our uniform histograms almost, if we were dividing it. For the most part, everything's about the same height. There's a little more 40s than there are anything else. So this is called an unordered. If we wanted to make an ordered one, we could. It's not very hard. All you do is write things in order. So I would record the 1 first, then the 8s, then the 9. I'd record the 4 first, and then the 2 9s. 2 5 5 8, 1 7 9. You're just organizing it so that these are all in order. 0 1 2, 2 6s, and then 9 9. And finally 2 4 4 7. This would be an ordered stem and leaf plot. It's nice for orders because you can see any time where you've got multiple copies of things because they show up right next to each other. This is exploratory data analysis, and it's about getting used to seeing how things work. And overall, I don't think it tends to be all that complicated. Now, there's a couple other types of data charts that we like to intend to discuss. So I wanted to sort of give you a brief sketch of them and maybe talk about some common advantages and disadvantages to seeing each of those types of data. So I don't know, maybe I'm taking a look and thinking about things. These are stem and leaves. It's very easy if you've got a large list of data to start to get a sense for how things are working. Maybe the most famous chart is a pie chart. So let's take a look at who pays for your college. Who pays for college? And a pie graph is maybe a very nice way to show the difference between what one person's doing and what another person's doing. In general, let me recommend with pie charts that you don't want to have too many pieces of it. If the pieces of the pie get too many, it starts to get complicated. But overall, in general, it costs for community college about $7,000 a year to run a community college per student. Who pays for college? By student. So let's say, I think the number that I recall reading from the Department of Education website, Google, I don't know, community college or something, $7,024. And in general, per student per term maybe. And in general, what I think the usual student fee was averaged across the country of all 50 states and all, I don't know, 5,000 something community colleges that we've got here. It was about this. Again, these are averages. Maybe your state pays more, maybe it pays less. So this is the total, and this is the student. So if I wanted to build up a pie chart of this, what I would do is I would take the student fee of 1122, and I would divide it by 70/24, and I would see that students represent just 15%. Let's round that up to 16 maybe, once I've got that in there. So 16%, what you do is you take the full circle and you figure out, well, this would be half. This would be 25%. So 16%, half of 25, this would be about 12% here. So 16 is a little bit more. So you give yourself a little rough estimate here. Of course, if you use Excel, you'll get something better. This is the part the student pays. This This is the part that not student pays. Now, of course, this was a very simple pie chart we've done. It's kind of nice because it shows that this piece right here is 16%. And it gives you a sense of the idea that the cost of running a college in terms of building construction, parking lot construction, paying for my salary, paying for my health and benefits, hiring custodians to keep things clear, keeping us in markers, all of these expenses that we've got cost quite a bit. And so usually the tuition fee at a community college is quite a bit less than what the total cost is per student. Pie charts are great for quickly conveying simple data, because you can take a look at this and say, ah, that's how this is working. So we do have pie charts, and they're really great for that. Again, we already talked about stem and leaf plots. You can also discuss bar graphs. And bar graphs are rather convenient. They're a lot like histograms, but they allow you to record qualitative data rather than quantitative. Remember, for the histograms, you absolutely have to have those class boundaries. Histograms let me do something else. Let me talk about quantitative data, but a bar graph, you can do anything. So a bar graph, for example, could look like this. This could have frequency, and this could have categories like male and female. And this could be a chart that was labeled mathematicians at VC. And if we were looking at the people who teach in our 4-credit math program, mathematicians at VC, let's say full-time faculty. And we're a fairly small community college, so 4, 3, 2, 1. You are looking at the only male math professor at Victoria College who teaches full-time at the 4-credit level. And right across the way, you've got my 3 colleagues who are the only female full-time faculty members who teach at the 4-credit level in math. I think we have a physics professor who might teach a class for us, but I'm saying mathematicians at VC who are full-time faculty. And of course we have a whole army of adjuncts, and we've got all sorts of people that even not full-time credit level faculty. But there you go. This is a perfect example of a bar chart. Notice I don't have these pieces right next to each other. That doesn't make sense. This is not a histogram, it's a bar graph. Notice that my labels are very qualitative things. They're not very much in the way of numbers. I can't distinguish that way. You could do all sorts of things. You could talk about Ford Motor Sales versus Chevy versus, I don't know, Toyota. You could label many things with a bar graph. You can also turn bar charts on their sides, and sometimes that's interesting. So I'd have male or female, and then I could have numbers of people that were doing different things. So you can have bar graphs, and that's interesting. Regardless of what your chart is, some things you should look out for. If you're not going to label in even units, then you need to remember to use squiggle. And that's what that symbol is called, squiggle. So remember that from last time. Here I am using even units, so that's okay. But if you're not, you need to remember to use units. Secondly, no matter what you're going to label your graph with, you should have a very clear sense of what all the pieces mean. You can never not label things. You need to know 1, 2, 3, 4, that doesn't mean anything until I tell you frequency. That lets you know this is an actual head count of mathematicians in the department. I need to label my x-axis as well, male and female. You need to know what these different groupings are. Proper labeling, because otherwise it's up for interpretation, it's up for grabs, and that makes it a little less than ideal. This pretty much wraps up for us the discussion of graphs. Let me strongly encourage you to try typing some of these graphs into Excel and playing around with the beautiful charts that it can make. Those charts are very easy to pop into a PowerPoint presentation and make something very classy come up quite simply. And that's a very nice thing to do. But I do have a little bit more time in this lesson, and what I wanted to do for you in this moment is to sort of outline how I think class should work. And what I mean by that, I guess, is let me talk to you about tips and tricks for studying math. Things that I've learned over the years, and I want to say it's hard-earned knowledge. This is not some pithy statement that I just randomly throw out there. I am not a good mathematician. That didn't just magically happen. Instead, I'm a practiced mathematician. It represents a lot of hard work. And maybe you can see some of that hard work on the sides of my wall here, little portfolios of things that I keep up, mostly to motivate myself to remember practice really does pay off. So let's first of all talk about some ideas behind mathematics education. I am not good at math. That's a statement, and it's a statement I've heard a lot. And just go ahead and raise your hand if you've ever said that about yourself. And please notice my hand is up. I am not good at math. Let me tell you a story. I will protect this person's name by calling them just my 6th grade mathematics teacher. But my 6th grade mathematics teacher did these things called speed drills. Little cards, and I don't know, would have numbers like 6 plus 5 divided by 32 times 12 minus 11 plus 10 times 18 divided by 7 equals, and then the first person to raise their hand up would get called and they would have to spit some number out. And I can't do that. It's not going to happen. I will never be that practiced in mental math. That's not my forte. And it doesn't need to be. But because of that, I became convinced in 6th grade that I am not good at math. I believed that about myself. And if you looked at my math scores, from there on out, once I got that negative thought in my head, you might start to believe it about me too. This is an example of what I call negative thinking. And here's what I want you to do with that negative thinking in your mind. I want you to delete it. No matter how much trouble you're having with a particular problem, no matter how terrible a particular word problem makes you feel, the instant your mind starts to say, I'm not good at math, I can't do this, I don't feel like it, I can't, I won't, I shouldn't, I mustn't, delete that. Let it go. Take a deep breath. And start to think, how will I succeed at this problem? Reprogramming your minds to be positive about math, I believe truly is the first step. Because I spent years of my life believing this. Let me tell you how much I believe this. That nameless 6th grade professor had me come to his office, sat me down, and told me, you should think about occupations that don't use math. Now, consider the irony of that, now in hindsight. Decades later, I can't quite show them, but they're right above me, and I sometimes imagine taking these diplomas to this dude. But I have a master's degree in mathematics. I have a master's degree in business, which requires a lot of mathematics. I teach statistics, and I have a statistics consulting company. And someone sat me down and said, you should think about jobs that don't do math. And in fact, every dollar I've ever earned ever since I quit working at UPS and the night shift to pay for college has been math. And I want that for you too. And it starts here with deleting negative thoughts from your mind. And you can jumpstart yourself years ahead of me just by doing that. Secondly, everything that you ever compare yourself to with math is different. Because here's the next phrase that I usually hear. I am great at English. And you can throw in something else besides English, history or art or music, something like that. But the point is this. You have practiced English a lot more than you've practiced math. You can't drive down the highway without reading a billboard, and that's secret English practice. And if English is not your first language, that's fine. It's not mine either. And you have this ability to learn other languages and eventually decide, okay, I have practiced my language a lot, because you have to do it every second of every day. There was a study done. It was done in Germany. And what their goal was to consider what world-class performance was truly like. And this is a very famous study. But here's what they did. They took children. They weren't very young. In Germany, it's a little bit different than how education works in the United States. They sort people, and already sort of by the high school age, sometimes you can get sorted into specific targeted degrees. So I think maybe until I actually enrolled in college, I never had a particular degree plan. But in Germany, you can get your degree plan a little bit earlier. So they took children who wanted to go into music. And the first day that the children came to this academy, and this was a live-in academy, so they knew that they were able to follow these children for the next 4 years of their lives. The first day they came in, they had the children go into a room, play a piece of music. I think it was a piece of music that they had practiced and felt good at, and then they were given some random piece of music from a list of things that they had never played. And people who couldn't see the children physically sat outside and listened. And these people were considered music experts. And they had to sort the children into 3 categories. One was world class. They said this person will be able to make a living doing music on the world stage. They will tour in a symphony. They will be some sort of rock star, whatever their particular type of music was. These experts said, this person's world class. The next group was people who would make their living doing music, but it wasn't going to be world class. Maybe they would be a music professor at some school, or maybe they would be able to do music teacher. The point was, this middle category of people were very good musicians, of course. They weren't world class, but they made their living doing music. And then lastly, there was the group of people that they labeled music amateurs. Maybe they would teach some piano lessons in their neighborhood. That would be okay. But the bulk of their income was never going to be from music because they just weren't quite there. Every child in this study for several years was ranked by these folks into these categories, but no one told the children. The children didn't know why they went into this room and played. Once they were done, they were followed. Not in a creepy stalker way, but just as follow-up to the study, to ask them later on, where do you make your money? So first of all, they're sorted by, at the beginning, early. This is the first listen. At the end, when they were just ready to leave their school, they were recategorized . And once this happened, this recategorization happened, then they were also recategorized into these groups. And here's the fascinating thing that was discovered. The difference between this first listen and this second listen. You might have thought that most people in this category went straight to here, and most of this one went to here, and most of this one went to here. That's not true even a little bit. There's no connection between these two lines that made any sense. However, on leaving, and then 10 years later when they followed up with them in the real world, there is a very strong connection between these things. So people can recognize final world-class performance as it's ready to hit the world. So it's not the fault of the listeners. So why don't these lines match up? Well, over the years that these students spent practicing and studying, they found something. Everyone. Because this was an elite music academy, of course, that we were going into, everyone spent hours studying. If you just looked at the time spent studying, you couldn't distinguish either who would become world-class and who wouldn't. but the word study is just a little bit vague. Studying can actually be sorted into two different types of activities. It can be repetition, it can be work, and everyone did at least this much. They repeated things to gain further skill. They worked hard. Not a one of these students, no matter which of the three categories they were sorted into, could be called lazy or slacker. That's important to keep in mind. But the ones who became world-class performers, every one of them did something else. They did what the study people call deliberate practice. Deliberate practice is different from practice as normal. Deliberate practice means you focus on just the pieces that make you stumble. Deliberate practice means that you look at the stuff that's just a little bit beyond your skill level, and that you strive to reach it. Deliberate practice involves this word grit. And grit is a very powerful predictor of human success. There's a movie called True Grit. I think John Wayne maybe. Grit is that ability that when you get knocked down by life, you come back up and you're ready to go again, no matter what. And grit is essential to deliberate practice because deliberate practice requires focusing on your weaknesses. When you practice deliberately, you only do the things that you're worst at. It's the difference between reading the first sentence in the first chapter of your book 50 times before the test because you swear you're going to read through the whole chapter, or going back to the last quiz and looking at just the problem that you made mistakes on. It's the difference between pounding your head on the homework again and again and again, or reading through the whole book and watching the videos and sending off some emails to get a sense of just what it is that you're missing. Every one of my students who tries is a hard worker. I would never accuse any of my students of not being hard workers. However, I do think that because of a misconception in America, possibly, how we think about studying, this vague word, that a lot of my students aren't practicing in the most effective way. You go back and solve a problem you already know. We call this a confidence builder. Who cares? You need self-confidence. That's important. It's terrifying. You have no idea how odd it is to be staring at a camera as I'm trying to look through the camera into your eyes, and then I think of all the eyes watching me, and I'm like, that's kind of creepy. You need self-confidence, but you need the self-confidence in terms of this grit. You need to go out and learn Excel on your own, even though it's not part of this course officially, because that's going to help you see things from a new perspective. It's going to help you become world-class. Every one of these groups spent 10,000 hours of study, and 10,000 might be a very famous number. But it's 10,000 hours of deliberate practice that truly makes someone world-class. And that's what you need. Now, of course, you're not going to get 10,000 hours of practice in this course. Instead, here's how I suggest your practice go. And I'm going to say this here, and I think I've said something on my website, and maybe those numbers are just a little bit different, but I think they'll be close enough that you get the gist of it. First of all, spend about an hour each week reading the week's chapters. Now I say read, and I really do mean just read. Read through the paragraphs, read through the examples. If you want, you can have your calculator by the side and calculate through some of them, but in general, we don't really cover all that many pages that you couldn't read through it, and just try to get a sense of what's happening. Next, it's not quite 3 hours, but spend about 3 hours watching these videos. get my take on it. Hopefully, after my years of experience, I'm able to suggest something clever to you or present things from a particular point of view. Once these things have happened, then you start to get a sense of what's going on. At that point, it's time to spend, I don't know, 1 to 2 hours solving the examples. This is key. Go back into the chapters that you've read, find all the examples in those chapters. This time for sure, have pen and paper, pencil and paper, and your calculator, maybe Excel up, and work through every one of those examples line by line. I did this too, so I'm not accusing. I'm just saying this happens. I remember a time saying, my goodness, I can't understand what this math book says. I'm just going to have to skip right to the homework because those examples, they just confuse me. Don't fall into that trap. No matter how hard it might be to read the book and solve their examples, it's a lot harder to solve an exercise when you've got nothing to go on. Also, easy as it might be to come up with your own idea about how things work, and maybe you can solve the example, possibly, and get the right answer, you may have got the right answer for the wrong reasons, and that's very risky. If you get the right answer for the wrong reason, then possibly you're not going to understand a later concept. So, spend a couple hours solving the examples. It lets you make sure you're using your calculator correctly. It lets you make sure that you've successfully plugged numbers into Excel because you know what the answer should be. It lets you see any insight that the authors have decided to give. And they'll have a different perspective than mine. So together, you'll be ready. Then it's time to start solving. I don't know, maybe this should be an hour or so. On my website, I generally have some selected recommended exercises, so solve exercises. And also, I don't know, spend a couple hours on our course website. Get into there, start working on the homework, start working on the conceptual stuff that we've got. We're up to 9 hours now. If you're on one of my face-to-face classes, of course, you're going to be spending 3 hours in lecture. And I don't really lecture in my face-to-face class. Instead, you're practicing stuff with groups of people and whatnot, practicing some of these solved exercises, so this ties into here. But the point is, by the time you come and see me face-to-face, you've already gone through this material a couple of times, and this lets you spend the valuable time that you actually have, and forgive me for my lack of humility, an expert in front of you, asking questions. That's the real thing you need. Trying stuff, failing, hopefully, but failing where I can see you so that I can help you have some grit and pick yourself back up. If you're in my online class, we don't have this. Instead, you're going to have to feel bold enough to email me. And that requires getting into this early enough that you're not emailing me seconds before your assignments are due. If you do all of this, it should only take you a couple hours to actually wrap up the true homework exercises and be ready to take the quiz. If you spend more time at the beginning gaining understanding, then when you actually tackle things at the end, it doesn't become all that difficult to solve the homework. The conceptual stuff in Aplia won't be all that complicated or difficult. So spend 2 hours wrapping up homework and quizzes. And then I always say about 30 minutes in office hours, or for the online students again, email. What are office hours? It's very scary to come into my office. I don't know exactly why, but there's this little force field barrier that keeps people out. But office hours aren't a bad thing. They're a chance for you to come and ask some questions. And oftentimes I see students who want to do well. They come into my office hours and they're just thinking to themselves, somehow this dude's going to magic all my problems away. And I wish I could. But that's usually a little bit beyond my skill level. Instead, if you've done all this work, when you come into my office, you're going to have some specific questions. You're going to be able to converse with me about what's happening. You're going to say, look, here's what I'm trying, here's what I've tried, it's not working, why? And that makes it, one, very easy for us to have a nice brief conversation. It makes it very easy for us to quickly get to the heart of the problem. We can focus on the complicated sides rather than trying to discuss how you add two numbers together and divide properly in your calculator. All told, I think this adds up to about 14.5 hours a week. And I would have to say that's about right. That's approximately the minimum amount of time that you need to spend to earn a usual grade, maybe a C. If you think you're one of those people who you always say, math is hard for me, you probably need more time. If you're one of those people who math is super awesome for, you can probably get away with a little less. But on average, 14.5 hours a week is about what it takes. And this is a rough example, of course. If you're in an online class, maybe this 3 hours of lecture is additional time you spend reading through the book more cautiously, working some examples. And if you're in the face-to-face class, maybe this hour of solving exercises doesn't quite have to happen because you'll do some of that inside of the class period. And maybe you'll spend more time on the online homework. So these are rough guidelines, but this, I think, is truly how to succeed in a mathematics course. This is the formula for success. It's that deliberate practice. And maybe I should squeeze in here one other thing and still somehow, I don't know, cut some time off of something. Make this just 1 hour. Put in 1 hour in here to revise. This class is cumulative. And like all math classes, statistics builds on itself. So if you're weak on something from before and you try to get a new concept, it's going to be difficult, if not impossible. So spend an hour of going back into the quizzes and saying, what didn't I get? Spend an hour of solving some old problems just so that as the weeks go by, you always maintain fluency in both the old concepts and the new. And as always, feel very comfortable coming to my office hours or emailing me. That's the biggest, importantest thing you can do. All right, I think I'm good enough for this time. I will see you next time in Chapter 3.